Good morning, all of you. In today's session, we are going to start with CSIR NET JRF Chemical Science, December 2014, Part C, Series 6. Earlier, we completed detailed solved question paper of the CSIR NET JRF of June 2014. Entire solved question paper is available on the channel called World of Competitive Chemistry. In addition, we already solved the previous year question papers for the academic year 2015, 2016, 2017, 2018, 2019, and 2020 as well. Both the sessions, including June and December question papers, all the solved question papers are available on the channel called World of Competitive Chemistry. This kind of standard previous year question paper discussion will fetching you towards any competitive examination you are preparing for, and also if any entrance examination, if you are really aspirant about any research, so in that case also it will be fetching to you. Let us enter into our actual today's concept. Right. CSIR NET JRF Chemical Science December 2014, Part C Series 6 consists of questions from 121 to 130. Let us start with question number 121. For a gaseous reaction, 2NO gaseous plus chlorine gaseous gives rise to non-linear transition state and in turn converted into 2NOCl. Pre-exponential factor in the rate constant is proportional to, right? So pre-exponential factor, the relation between the pre-exponential factor and so that should be predicted from this reaction. So we are going to carry the reaction between nitric oxide treated with chlorine. It proceeded with the transition state, which is a non-linear one, and the formation of NOCl, nitrosyl chloride, will be possible. In this case, what will be the relation between rate constant with respect to temperature? For that purpose, here, in accordance with the collision theory, K2 is given as a P into sigma into 8 kBt 1 by 2 pi mu experimental minus EA by kBt. EA denotes activation energy, K proportionality, and the T is the temperature and the Kelvin scale, right? So in accordance with this one here, rate constant and the temperature both are related with these two terms are related with K2 is directly proportional to T to the power 1 by 2. So K is directly proportional to T to the power 1 by 2. This will be the right answer. So let us get more information about the pre-exponential factor. Pre-exponential factor is mainly defined by the symbol called A, and it is an important component which is given in the Arrhenius equation. Arrhenius framed this kind of formulation, this kind of relation in 1889. Is the chemist from Sweden, and pre-exponential factor, also known as a frequency factor, which is symbolized with A and represent the frequency of the collision between the reactant molecules at a standard concentration. So for this reaction, rate and temperature both are related with the K2 is directly proportional to T to the power half under root T. That is provided in the option number 1. For question number 121, option number 1 is the correct answer. Let us move on to question number 122. Species A undergoes a unimolecular reaction as follows. A plus A gives rise to A star plus A. One is excited and second is in normal ground state. And this reaction proceeded with K1 rate of the reaction. And being it is a reversible, the product get converted into a reactant through K inverse rate constant. And this A star can be converted into product through the mechanism, and the rate follows the K2. For this reaction, first order rate constant at high pressure is denoted with K infinity. First order rate constant is denoted K1 is nothing but K infinity, and the first order rate constant becomes K infinity by 2. First order rate constant becomes K infinity by 2 when pressure is halved. When pressure is halved, the K infinity, actually it is denoted for the first order kinetics K1, and if we are going to halve the pressure, and consequently this K infinity also got halved, K infinity by 2, right? So that is provided in this first order rate constant graphical representation. When we are going to plot the graph between k infinity by 2, which are taken in the y coordinate, and p pressure taken on the x coordinate. You can observe one kind of hyperbola structure wherever you can find the maximum length that is taken as a k infinity, where first order rate constant it will be. When we are lowering the pressure as a 1 by 2, so that here rate of the reaction also got halved. So at that point k1 will be, the value of k1 will be, so k1 is nothing but what? K1 is nothing but first order rate constant that is denoted with the k infinitive. So if we take the point on this hyperbola at this instance where pressure got halved, consequently k infinity also got halved. That's the reason why if you want to calculate the k1 value, we have to take the ratio of these two, k infinitive by a 1 by 2. So k infinity by a 1 by 2, this ratio will become k1. So let us see the detailed description about this equation. So this reaction stepwise mechanism was clearly explained by the scientist called Lindemann, and it oftenly known as Lindemann-Hinshelwood mechanism. So Lindemann-Hinshelwood mechanism is mainly this is discovered by Lindemann and Hinshelwood in 1921. So development was carried by Hinshelwood, and a breakdown of the reaction into the different steps, different elementary steps were given by these two scientists, and for each step they denoted one kind of rate of the reaction. So for example, if a plus a gives rise to a star plus a, the forward reaction proceeded with the rate constant called k1. If you want to go with the backward reaction, if you want to observe the backward reaction, that is denoted with k inverse, and whatever a star got generated, that will be converted into the product through the rate constant 2. So this breakdown of the complete reaction into different elementary steps, which is given by the scientist called Lindemann, and this data was collected from chemistry library text. Okay, and if you want to calculate the rate of reaction dA by dt, dA star by dt, rate of this transitory compound generated within the reaction, so that is given by k1 concentration of A into M, that is nothing but forward first step reaction, minus k inverse A star into M, this is the rate constant for first order reaction for backward reaction, minus k2 into A to the power star, A to the power asterisk. So this is nothing but forward reaction in the second step, right? So in this way, interrelation between all these are possible. So what they are asking for, the first order rate constant becomes k infinity by 2, and when pressure A becomes A by 2, for if this is the condition, then what is the value of k1? K1 is nothing but when the starting materials got converted into one transitory compound, that forward reaction, step 1 reaction, is denoted with the k1. So that k1 at this particular instance on this hyperbola is taken by the ratio of k infinity by a 1 by 2. That means a concentration of A will be halved, because within the problem they mentioned we are taking the pressure concentration of this starting material as half, right? So if we take this ratio, that value is equal to k1. This is in accordance with Lindemann-Hinshelwood mechanism. So for question number 122, option number 1 will be the correct answer. Let us move on to question number 123. The low and high temperature limits a vibrational partition function theta is equal to h nu by k. Here, low and high temperature limits a vibrational partition function to be depicted. So this is a question from vibrational partition function is nothing but physical chemistry of spectroscopic analysis, right? So vibrational energy levels of atomic molecule generally given by En is equal to n plus 1 by 2 h nu. This will be the empirical formula for the calculation of vibrational energy of the atomic molecule. So then nu denotes what the vibrational frequency, and n is the vibrational quantum number. So that may be 1, 2, 3, 4 like that. And in case it is easy to sum the geometric series as shown below. Geometric series is taken as Q vibrational is equal to summation is equal to 0 to infinity. These are the limitations. 0 to infinity, you are going to sum e to the power minus n plus 1 by 2 h nu by kt. Right. So here this can be expanded. How can we expand? Summation was taken, right? You can take the individual terms and all get added in this manner, so that the finalized equation will be e to the power minus h nu by 2 kt into 1 by 1 minus x will be taken, where x value is e to the power minus h nu by kbt, whose value is less than 1. So in this case, Q vibration is calculated as e to the power minus h nu by 2 kt by 1 minus e to the power minus h nu by kt. So this is the vibrational energy. At low temperature, this vibrational partition function value is given as e to the power minus theta by 2t. At high temperature, the value will be t by theta e to the power minus theta by 2t. So for question number 123, option number 2 is the correct answer. These two are the limitations we are applying. So low temperature, the value will be e to the power minus theta by 2t. High temperature, the value will be t by theta e to the power minus theta by 2t. So here, for question number 123, option number 2 will be the right answer. Let us move on to question number 124. The probability of finding the harmonic oscillator in the energy level n is equal to 1 is neglect the 0 point energy and assume h nu is equal to kbt. Probability of finding the harmonic oscillator when we are taking n is equal to 1. N is equal to 0 is called the 0 point energy. We are going to next level, n is equal to 1. In that case, probability of finding the harmonic oscillator energy that to be predicted, right? So the quantum harmonic is oscillator. What is meant by harmonic oscillator first? Harmonic oscillator is nothing but a quantum mechanical analog. It is a quantum mechanical analog of the classical harmonic oscillator. So initially classical chemistry will be there. When we apply the quantum mechanics of that one, it will be regarded as a quantum harmonic oscillator. Because of arbitrary smooth potential can usually approximated as a harmonic potential. So harmonic potential can be employed for this kind of harmonic oscillator. And most important model systems are quantum mechanics. So in quantum mechanics, we are going to apply these quantum harmonic oscillators. Relative probability of finding any interval dx just inverse of the average velocity over that interval. For the quantum mechanical case, the probability of finding the oscillator interval dx is a square of the wave function. Simple harmonic oscillator, kinetic energy can be calculated as 1 by 2 mv square. So total energy is given by kinetic energy plus potential energy. Kinetic energy just now we discussed 1 by 2 mv square, and the potential energy is given by 1 by 2 kx square. What is kinetic energy? What is potential energy? Kinetic energy is nothing but the energy which is imparted due to the motion, and the potential energy is nothing but when the energy associated when that object is in the stagnant condition. So when we sum these two, that the total energy will be imparted. Then what is meant by 0 point energy? The lowest allowed energy when n value is equal to 0, that is denoted as a 0 point energy in the quantum mechanical oscillator. E naught value is calculated as h cut omega square. Then they are asking for first order. So one-dimensional harmonic oscillator when n is equal to 2, entire equation can be regarded as wave function. Psi x is given by 2 into 2 pi to the power 1 by 2, x naught whole to the power minus 1 by 2 into x by x naught e to the power minus 0.5 into x by x naught to the power 2. So this will be the equation for first order kinetics. Right. So n is equal to probability of finding the harmonic oscillator energy, that will be is equal to e to the power minus 2 into e to the e minus 1. This will be the final answer. For question number 124, option number 4 is the correct answer. Let us move on to question number 125. A particle in one-dimensional box of length L is perturbed by delta functional potential, delta x minus L by 2 in the middle of the box. The first order energy correction to the ground state will be, first order energy correction is required for this. Again, it is a question from physical chemistry, and you can say it is a quantum mechanics. Particle in the one-dimensional box to be regarded. Here, one of the hint is given, integration limitation from plus infinity to minus infinity was taken. Fx dou x minus a into dx is equal to fa. This will be the relation between function x and function a. So here energy of ground state is given by integration 0 to 1 psi x star dou x minus L by 2 psi x and dx. So when we apply this, when we derive this, it will be extended as integration 0 to 1 under root 2 by L sine n pi x by L s into x minus 1 by 2. X minus 1 by 2 value is 0. When x minus 1 by 2 value is 0, this entire term, denominator term, will become 0 itself. Only the requirement is 2 into sine square pi L by 2 Lx will be taken. So if we cancel all the common terms, the final equation will be 2 by L is provided in the option number 4. For question number 125, option number 4 is the correct answer. Let us move on to question number 126. The operator s plus or minus are defined by s plus or minus is equal to sx plus or minus isy. Sx and sy are components of the spin angular momentum operator. Again, it is a question from physical chemistry. The commutator sz and s plus is commutator sz and s plus can be calculated. Here, the relation between the sx and isy is given. Sx and sy denotes what? Spin angular momentum operators in xy coordinates. S plus or minus value is given to us. The commutator of sx and sz and s plus to be predicted. For that purpose, the relation given here, what are the parameters sz and s plus value to be predicted? S plus or minus is equal to sx plus isy. This is the given parameter in the problem. Sz comma sx plus isy. So we can take the sum of these two. Then it can be extended as ihsy plus I into minus ihsx can be taken. If we cancel, so what happens? ihsy plus I square sxh can be taken. So if we expand this equation, now in both the sides we have h as a common term. So that h taken as the common, then sx plus isy. This sx will be taken, isy will be taken, then sx plus isy. What is the value? That is s plus or minus 1. Then h cut s plus can be taken. So this term is we can substitute with the s plus. H cut s plus is the value of commutator. H cut s plus is provided in the option number 1. For question number 126, option number 1 is the right answer. Let us move on to question number 127. The quantum particle with the fixed initial energy E naught is less volume is allowed to strike the following 4 barriers separately. The transmission probability is maximum in. Transmission probability is maximum in, right? So we are taking 4 different barriers. Into these 4 different barriers, we are able to pass the particle. Quantum particle is allowed to move through these particles. So when the particle is moving through these barriers, where the transmission probability will be higher, that to be predicted. So it is moving from this direction. The diameter, length of the barrier is denoted with a V, and the area of diameter is given by 2a in option number 1. In the option number 2, here we are going to start with the quantum particle which allowed inside, and here the length is given by V and area is given by A. So in the third case, length is given by 2V and area is given by A. So length is given by 2V and area is given by 2A in the option number 4. For this purpose, here we have the transmission probability. Transmission probability is equal to e to the power minus 2 under root 2m VEL. So this is the equation for this transmission probability. Now, there are 3 different possibilities are there. Value of M can be raised and the temperature can be raised, volume can be raised and temperature lowered, and the volume can be raised and temperature lowered. So these are the three probable conditions we are going to employ. So when this is a condition, so when the length taken as a V and the area is taken as area of diameter taken as A, in that condition, transmission probability will be very high. In this case, it will be maximum. So here, question number 127, option number 2 is the correct answer. Let us move on to question number 128. Given the following two relations, x1 d mu1 plus x2 d mu2 is equal to 0. x1 d v bar v1 plus x2 d v bar 2 is equal to 0. For the binary liquid mixture at the constant temperature and pressure, the true statement is that. So in this case, what are the true statements? So first case, you can directly deduce it from Gibbs-Duhem equation. Gibbs-Duhem equation is the summation I xi d mu I is equal to 0. Xi d mu I is equal to 0. So they are taking summation. If we expand, what happens? x1 d mu1 plus x2 d mu2, because two relations are given for binary mixture. Binary mixture is nothing but two liquids are going to combined. So for that purpose, here two parameters only combined. One is x1 d mu1 plus x2 d mu2. So that is available in the in this equation. So in this equation, we got this. Gibbs-Duhem equation. That's why relation 1 is correct. And for this equation here, temperature and pressure variables are taken as constant terms, where xi denotes what? Kilomole fraction, eighth component. Xi is nothing but kilomole fraction of the, that is the mole fraction of the eighth component. Eighth component mole fraction is denoted with xi, and this equation can be employed at a constant temperature and pressure term. So that Gibbs-Duhem equation can be verified in the equation A. When we are taking same equation in terms of volume, x1 d v bar 1 plus x2 d v2 bar is equal to 0. This also verified by Gibbs-Duhem equation. So here these would be employed for binary liquid mixture at constant temperature and pressure, right? At constant temperature and pressure conditions, both are applicable. That's the reason why for question number 128, both the relations are correct in accordance with Gibbs-Duhem equation, right? So for question number 128, option number 1 is the correct answer. Let us move on to question number 129. If the bond length of heteronuclear diatomic molecule is greater than the upper vibration gap between the successive absorption lines in the p branch, right? I took this information from Ed Uncle. Thank you very much for providing the information. So in order to solve this problem, first, heteronuclear diatomic molecule energy levels, vibrational rotational energy levels are provided as Bj into J plus 1 plus V plus 1 by 2 omega bar minus Xe into V minus 1 by 2 bar omega bar. So here all the units are mentioned in terms of meter inverse, where B is called a rotational constant whose value is h by 8 pi square IC, right? So this will be the constant value which is provided for rotational constant, which can be substituted in this, right? So J means a coupling constant, nu is the vibrational frequency. So in this manner, we energy vibrational rotational of diatomic molecule can be calculated. Then it can be regarded as B is equal to h by 8 pi square mu r square C. So here I value can be replaced with this pi mu r square, so that the equation can be expanded. B is equal to h by 8 pi square mu r square C, where r is the bond length, radius, bond length it is. And if the bond length of heteronuclear diatomic molecule is greater in the upper vibrational state, the wave number corresponds to the p branch linear. So here, so in terms of P branch, the energy is given as delta E vibrational rotational is equal to delta E denotes what? Energy transition between the two consecutive energy levels. It is given by omega bar into 1 minus 2 xe minus 2b plus j prime b minus b prime into j prime plus 1. J prime denotes rotational quantum number for upper vibrational level. So if it is a ground state, it is indicated with a B. So prime indicates what? It is the upper energy level. Then P prime denotes a rotational constant in the upper vibrational level. So J prime is the rotational quantum number for upper, and B prime is the rotational constant for upper vibrational state, right? So here rotational quantum number is J, rotational constant is B. So those can be substituted in this equation, right? As the bond length R increases, B prime decreases because both are inversely proportional. So bond length and B prime values. So gap between the successive absorption lines in the branches increases non-linearly, because for this P branch, it will be proportional to 4B minus 2B prime. P branch, two successive P branch lines are proportional to 4B minus 2B prime. That's the reason why it will be increased non-linearly. That is provided in the option number 1. For question number 129, option number 1 is the right answer. Let us move on to last question of the series. EPR spectrum of free radical containing nuclei with non-nuclear spin is obtained if the following selection rules are observed. EPR spectrum for free radical to be considered, and the nuclear spin will be taken as a non-zero. If nuclear spin taken as a 0, that will become ESR inactive, because the spin is required for that, because when it is in odd electron state, then only that is used to impose the paramagnetic nature, and then only that molecule becomes EPR active, right? Let us see. So electron paramagnetic resonance, electron paramagnetic resonance, alternatively known as electron spin resonance also. This is the method in order to study the materials which is associated with unpaired electrons on that, right? Since the magnetic field interacts with the spin of the system has to become a non-zero. Because of this reason, the system having free electrons or unpaired electrons are required in the spectroscopic study. So when unpaired electrons are present, then only they are used to give the spectral lines in the EPR spectroscopy by employing the formula 2Ni+1 formula, right? So here transition between these levels governed by magnetic dipole moment, that is given by delta S is equal to 0. Means spin retention is required. Means whenever any molecule is excited in the ESR spectroscopy, if in the ground state it is with the clockwise rotation spin, after the excitation also that should be in the clockwise rotation. Spin retention is required. So spin variation is not required. So delta S is nothing but transition from lower energy level to higher energy level. The spin value should not be varied. Initially, if it is plus half, after the excitation also plus half. Initially minus half, that should be minus half in the excited state also. Spin inversion is not at all allowed. And delta L is nothing but angular momentum value. Angular momentum value can be plus or minus 1. Means one energy level to another of higher, otherwise another energy level of lower can be allowed, right? So a delta L value can be plus or minus 1. Angular momentum value can be either raised or lowered by 1 unit. So these two are the selection rules which are applicable for spectroscopy. So delta mu S taken as a delta mu S taken as a plus or minus 1, delta mu L taken as a 0. Delta mu S taken as plus or minus 1, delta mu L taken as a 0. So this can be applied for EPR spectroscopy. That is available in the option number 2. For question number 130, option number 2 is the correct answer. By this entire series of CSR NET GRF chemical science, December 2014, part C series 6 was completed. So we will come up with the next series in order to complete this entire CSR NET GRF chemical science question paper. Thank you very much for your patience listening, and I think this will be helpful for your preparation. Thank you one and all.